classmates, in this class, we will learn about selection of blank reference together. First, let's understand the common types of blanks, mainly profiles, castings, forgings, and standard parts. Let's first learn about the first type, profiles. Profile refers to materials such as steel, non-ferrous metals, or plastics that are produced through methods such as pulling, extruding, and pressing, and have a constant cross-section along the next direction. After cutting, profiles can be directly sent to the workshop for surface processing as raw materials. Profiles are the main source of raw materials for mold parts, including steel plates, round steel, pipes, and other types. The second type is casting, which is suitable for making complex mold parts with complex shapes, especially complex rough castings that are difficult to form by other methods. The shape of the blank is complex, and the vibration absorption is good, but the mechanical properties are low. Typical castings mainly include steel castings, ductile iron castings, aluminum castings, etc. In the mold parts, some upper and lower modules of the stamping die will use castings, and other mold parts are rarely used. The third type of forging refers to the blanks obtained by forging metals in batches. The forging have good mechanical properties, high strength, and impact toughness, but are complex in shape. Typical forgings mainly include shaft forging and flanges. Forging are suitable for making blanks of die parts with high strength and special structure in molds. The fourth type of mold semi-finished or standard parts refers to standardized parts manufactured according to national standards and issued standards, such as mold frames, guide columns, guide sleeves, gate sleeves, etc. These standard parts can be directly purchased from the manufacturer, processed on the forming surface and related parts, and can be used, which can greatly reduce mold costs and shorten cycles. Second, selection of blanks. How should the blank be selected? We mainly consider the following aspects. First, the material and mechanical properties of the parts. Second, the structural shape and external dimensions. Third, the production type. Fourth, the production conditions of the blank workshop. Fifth, the possibility of using new processes, new technologies, and new materials. Third, concept and classification of reference. Next, we will learn about the concept and classification of references, the points, lines, and surfaces used to determine the position of other points, lines, and surface. On a part drawing, all actual parts are called references. As shown in the figure, the right end face of the stepped shaft is the reference for the stepped surfaces B and C in the next direction, and the stepped surface C is the reference for the left end face D of the part in the next direction. In the diameter direction, the diameter 40 is the reference of the outer circles 20 and 30 on the axis. References are the starting points for annotating design dimensions. References can be divided into two categories based on their different functions: design references and process references. Design references refer to the references used on part drawings to determine the positions of other points, lines, and surfaces. Technical references refer to the standards used in the machining, measurement, and assembling processes. Technical references can be divided into four types according to their different purpose: process standards, positioning standards, measurement standards, and assembly standards. Process reference refers to the reference used to determine the size, shape, and position of the processed surface in this process. Positioning references refers to the reference used to determine the correct position of the part in the machine tool fixture during processing. Measurement reference refers to the reference used to verify the dimensions of the processed surface and the positional accuracy between each surface. Assembly reference refers to the reference used in machine assembly to determine the correct position of parts or components in the machine. Fourth, selection of positioning references. How to choose the positioning reference? Whether the selection of the positioning reference is reasonable will directly affect the dimensional accuracy and the relative position accuracy of the machined surface of the part. The positioning reference must be selected correctly before processing. The positioning reference can be divided into rough reference and fine reference. The rough reference refers to the use of the raw surface as a positioning reference, and the fine reference refers to the use of the machine surface as the positioning reference. The requirement for selecting rough reference is to provide the necessary positioning surfaces for subsequent processes, and the following should be considered. Firstly, the principle of reasonable allocation of machining allowance is to use important surfaces with small and uniform machining allowance as rough references. As shown in the figure, the surface processing requirements for the guide rail surface are high during processing. Therefore, the bottom plane of the bed leg should be processed first before processing the guide rail surface. That is to say, the bottom plane of the bed leg should be processed first with the guide rail surface as a rough reference, and then the guide rail surface should be processed with the bottom plane of the bed leg as a fine reference, which is the processing method shown in Figure A. Secondly, ensure that the machined surface of the part has a certain positional accuracy relative to the non-machined surface. The processing of the sleeve is shown in the figure. The A surface of the outer cylindrical surface is a non-machined surface, and the B surface of the inner hull is a machined surface. There is a requirement for coaxiality between A and B surfaces. Therefore, using the A surface of the non-machined surface as a rough reference, the A surface is clamped with a 3-jaw self-centering truck, and then the B surface is machined to ensure that the machined inner hull is coaxial with the non-machined outer circle. Thirdly, select the surface with the smallest machining allowance as a rough reference, as shown in the figure. For the machining of the shafts due to forging errors, the coaxiality error between the large and small ends of the blank is 3 mm. At this time, the small end should be used as a rough reference to machine the large end first, because the machining allowance on the end that is machined first is larger. If the large end is used as the rough reference criterion, the small end will become scrap due to insufficient machining allowance. Fourthly, the coarse reference is usually only allowed to be used once in the same dimension direction, as shown in the figure for the stepped axis, since the rough reference is generally rough. If the rough surface B is repeatedly used for positioning, and then the surfaces A and C are machined separately, it will inevitably result in a significant coaxiality error between surfaces A and C. Fifth, the principle of easy clamping. Choose a rough reference surface and try to make it as smooth and even as possible for accurate positioning and reliable clamping. The key to selecting a precise reference is how to reduce errors, and generally should follow the following points. Firstly, the principle of reference coincidence is to choose the design reference of the machine part as the positioning references as much as possible to avoid positioning errors caused by reference non-coincidence. As shown in the figure A, when machine plane 3, if plane 2 is selected as a positioning reference, it conforms to the principle coincidence, directly ensuring that the size is a design dimension h2 plus or minus th2 or 2. When plane 1 is selected as a positioning reference, it does not conform to the principle of reference coincidence. As shown in the figure B, when the positioning reference does not coincide with the design reference, the dimensional tolerance of the design dimension h2 plus or minus th2 or 2 is not only affected by the dimensional tolerance th3 of h3, but also by the dimensional tolerance th1 of h1. The impact of th1 on h2 is caused by the non-coincidence of references, because when the references coincide, the machining accuracy requirements of the process are easier to ensure than when the references do not coincide. Secondly, the principle of uniform references should be followed. When there are multiple surfaces on a part that need to be machined in order to ensure the position between each surface, a uniform positioning references should be selected for machining with high accuracy. For example, most processes of shaft parts can use two-stage center hole positioning, using the axis line as the positioning references to ensure the dimensional and positional accuracy of each main machined surface. Thirdly, the principle of mutual references. When the positioning accuracy requirements for two surfaces are high, they can be used as references for each other and repeatedly processed to ensure the required positional accuracy. As shown in Figure A, during the grinding process of the guide sleeve, in order to ensure the coaxiality requirement between the inner and outer cylindrical surfaces of diameter 32H8 and diameter 42K6, the outer cylindrical surface of diameter 42 can be used as a positioning reference first, and the inner hole of diameter 32 can be machined on the internal grinder, as shown in Figure B, then using the inner hole of 32H8 as a positioning reference. Grinding the outer circle of 42K6 on the spindle can easily ensure that there is sufficient machining allowance on each machining surface. Achieving high coaxiality requirements as shown in Figure C. Fourth, the principle of self-reference. When the clearance of certain machined surfaces is small and uniform, the machined surface itself can be chosen as the positioning reference. Whether choosing a rough reference or a fine reference, a comprehensive analysis should be conducted based on the specific situation, and the key points should be grasped for a reasonable selection. In this class, we mainly talked about the selection of rough references. See you in the next class.